Hello, and welcome to this tutorial on the term structure of interest rates. The term structure of interest rates refers to the relationship among interest rates for different maturities, holding all else equal. So that means we would have the same borrower, the same currency, the same type of bond, all reflected here on the term structure. Close maturities typically will have similar levels of rates, but the shape of the curve and the slope can vary quite a bit. The chart on the right shows cyclical patterns that we would see. So the curve might be steep with longer maturities having much higher yields than shorter maturities. It can be inverted. It can be what so-called normal shape, which means modestly upward sloping, or it can be flat. So let's review the spot interest rate. The end period spot interest rate is the average compounded interest rate earned over end periods with full reinvestment earning interest on interest. So what exactly does that mean? So let's suppose we have a 2-year bond that pays a spot interest rate of 10%. That means $10,000 invested at that rate will be worth $12,100 after 2 years. So there's no intermediate cash flows. We've invested $10,000, earning 10%, and then we're earning 10% again. And that compounded rate will give us 12,100. To see it in a little more detail, you can look here at this table. And you can see that we've invested 10, we've earned 10%, that gives us 1,000. That's now our new balance. We're now earning 10% on that. And since that is a higher balance, we're earning 1,100 in the second period. And that's how we get to our 12,100. And this is reflecting the compounding of interest. Now, suppose that the 1-year spot interest rate is lower, 8%. So what rate would we need to earn then in year 2 to break even? So in other words, we're getting 8% for the first year in this case, and we want to still end up with 12,100 as we would if we invested at 10% each year. Well, we're starting year 2 with a lower amount, 10,800. And so the difference between this 12,100 where we want to be and where we start is the interest we need to earn that year, 1,300. And then we simply calculate what rate of interest that would imply. So we need to earn 1,300 on 10,800. So that means we need to earn 12.037% interest. So if we were to earn 8% in year 1, and then this rate in year 2, we would end up with 12,100, same as we would if we earned 10% each year. So this is a way of just showing the equations. So 10,000 earning the 1-year spot rate plus a forward rate or a rate in the second year, or earning 10% both years. Both of these leave us with 12,100. So this implies obviously that 1 plus the 8% times 1 plus the 12.037% must equal 1 plus 10%. In other words, we're saying 1 plus the 1-year spot rate times 1 plus this break-even forward rate must equal 1 plus the 2-year spot rate in order for us to break even. If we turn those into variables and solve for what we're trying to solve for, the break-even forward rate, we obtain this relationship here. 1 over R2 squared divided by 1 plus R1 minus 1. So let's see how that works. So if we plug back in the numbers that we'd started with, 10% and 8%, we will get to 12.037%. So you may want to pause here and just make sure you can do this calculation. Okay, so moving on, let's generalize. So this is the difference, the key difference between the forward and the spot interest rate. The spot interest rate is the compounded rate we earn over the full period, whereas the forward rate is looking at a sub-period in the future and looking at what the break-even interest rate would be for that period. So let's do some algebra now to generalize this. What we're saying here is that if we've got n-1 periods and we have a spot rate for n-1 periods, we will earn that spot rate compounded over that amount of time, n-1 periods. And if we then earn a break-even rate over the next period, the nth period, or between n minus 1 and n, that should break even then with the spot rate we would earn over n periods. So in this case, we're compounding Rn, which is the spot rate for year n periods or n years, if thinking years, versus the spot rate for 1 year less, and we need to calculate what this is. So we do some rearranging, divide both sides by the n minus 1, 1 plus the n minus 1 spot rate to the n minus 1 power, and subtract 1, and we will obtain this relationship. So let's see how that works with an example. Suppose we have a curve of spot rates. So we have a spot rate for 1 year, 2 year, and 3 years given as in this table. And this is the formula that we just derived in the previous slide. So what does that imply for the forward rates? Well, we just plug in 1 plus, so this would be, the first case would be 1 plus R2 squared. So that would be 1 plus 6.5% or 1.065 squared, divided by 1 plus R, okay, that's 2 minus 1, so 1 plus R to the 1 power, which means to no power at all. So we divide that by 1.055 and then subtract 1 from that ratio, and we get 7.51%. Applying the same formula now for the next period, we will be using the 6.25% and the 6.5%. Here, the 7.25% cubed and 1 plus 6.5% squared. And in this case, we obtain 8.77%. So you may want to pause here and make sure you can do these calculations. Okay, so now a little more algebra. There will be circumstances where we actually don't have the spot rates, but we have discount factors, like what we were talking about in previous slides. So how could we derive forward rates from discount factors? Well, let's start with the formula that we already derived for the forward rate coming from spot rates. Okay, so this is the same formula we just looked at. And recall the relationship between spot rates and discount factors. So the discount factor for period n is going to be 1 over 1 plus Rn to the n. So this is the spot rate for period n, and this is compounding for n periods. And if we do divide 1 divided by this, we will get our discount factor. Now that implies that 1 plus Rn to the n is equal to 1 over the discount factor, just by rearranging, essentially putting this up there and that down there. So let's substitute that in and rearrange further. So if we take this formula and substitute in this, both for the n and the n minus 1 case, we will get this. We can rearrange that, and we will get d of n minus 1 over d of n minus 1. Okay, so a very simple compact formula. So let's apply that. So here, let's suppose we have the discount factors. Now we also have the spot rates, but if we have the discount factors only, or that's what we want to use to calculate the forward rate, we should be able to derive the same forward rates as we did before using these discount factors. So let's do that. So in the first case, we're taking d of n minus 1 over d of n, so that's 9479 divided by 0.8817. Now notice the one before is on top and the one after is on the bottom. Okay, subtract 1 and we get 7.51%. And then in this case, we're doing 8817 divided by 8106 to get the forward rate between years 2 and 3. And that comes out to 877%. And those numbers should look familiar. They're exactly the same as we got when we derived the forward rate directly from the spot rates. Okay, so when we talk about term structure of interest rates, there are a number of theories that economists will frequently invoke. These are unbiased expectations, liquidity premium, and market segmentation. So I won't go into a lot of detail. There's a little more detail about this in the appendix if you're interested and in the textbook. But break-even forward rate essentially is implying that, unbiased expectations is implying that the break-even forward will equal the expectations for the future. So it's simply saying that the forward rates we derived as break-even forward rates are the market's expectations of what future short-term rates will be. Liquidity premium is saying, well, no, that isn't exactly right. The break-even forward rate should be higher than the expected future rates because there is a premium that the market or investors will demand to hold longer dated bonds. And so including that premium would imply a forward rate a little bit above the expected future rate. And then finally, there's a theory called market segmentation, which doesn't have a fixed relationship like we have here, but essentially says that each of these markets operate somewhat in isolation and reflect the supply and demand in those parts of the curve. Now, as I mentioned, there's more detail about this in the appendix and what evidence there is supporting the various theories. But for the most part, I would note that financial economists and market practitioners really don't spend a lot of time on these term structure theories. Why is that? Well, it's because the fair value of financial instruments are based on arbitrage pricing, and that doesn't depend on them. So looked at it this way, the forward interest rate is not necessarily predicting the future level of that rate. Certainly it will be influenced by the market expectations of future interest rates. So for example, if the markets are expecting rates to go up or down, let's say up sharply, that would be associated with a steeper curve, or down could be associated with an inverted curve. But that is not the sole driver. Rather, the interpretation here is that the forward rate is today's price for that interest rate. So another way of saying it is the forward rate represents what the interest rate for that forward period is today, and not necessarily being an unbiased predictor of what it will be in the future. So let's move on to a related topic, which is yield to maturity. Now, frequently, we're not dealing with spot rates. Spot rates are associated with zero coupon bonds or strips or any instrument that has a single cash flow, whereas yield to maturity will be what we see when we're looking at bonds with multiple cash flows, which is really what a normal bond would look like. So as we saw in a previous tutorial, we can value these future cash flows on a multi-cash flow instrument like a bond by discounting each cash flow at the appropriate spot rate. And in fact, that's what we did with our valuation exercise earlier, and that's really what's driving bond strips arbitrage that we saw in an earlier tutorial. Yield to maturity is different. It's essentially discounting all of the cash flows at the same rate. Now, that's not to imply that they all have the same spot rate, but rather we're looking at essentially the average rate. What is the yield to maturity? What is the rate that if we were to discount each of the cash flows at that rate for, of course, compounded for the appropriate number of periods, 1, 2, or 3 in this illustration, that would give us the same value. So another way of thinking of yield to maturity is an average of the spot rates for that particular instrument, reflecting the cash flows. So let's look at a problem to illustrate how this works. So you may recognize these numbers. These are the spot rates we were looking at before. So 5.5%, 6.5%, 7.25%, and we got discount factors from those. So let's say we want to know what is the yield to maturity for a 3-year bullet bond with a 5% coupon rate. Well, we would first need to calculate the price of that bullet. So we've got 5% coupon. So if we're dealing with a $100 face or 100% face, we take 5 times each of these discount factors because we're going to earn it in year 1, year 2, and year 3. And then we're going to add to that the 100, the repayment of principal, times the year 3 discount factor. So summing all of that together, we get 94.261. Then we want to use our financial calculator to calculate what is the average yield for a bond that had this price and had these payments. So we have input 5 here for payment, representing the coupons, and 100 for the final payment of principal. We put in minus 94.261. Remember that the sign of this has to be the opposite of the sign of the payments, since we're either paying for this and getting this, or the opposite. And of course, it's 3 years. We then hit compute, and we get 7.19, and that means, of course, 7.19%. Now note, this is a 3-year bond. but it doesn't have the yield to maturity equal to the 3-year spot rate. It's a little bit less than the 3-year spot rate. And we will generally see it will be less in an upward sloping curve like this. So it is essentially reflecting the fact that some of the cash flows are getting the spot rate down here. So that in that sense, it's an average. But since we're getting the principal in the final year, that weighs even more heavily. So generally, you would see the yield to maturity on a bond of n periods, 3 periods in this case, similar to the spot rate, a little bit less if the curve is upward sloping. If the curve was flat, actually they will be the same. And if the curve is downward sloping, this would be a little bit more. Let's look at another example to show how it varies. So let's say we're looking at another 3-year bullet bond with a 15% coupon. So again, we have to calculate the price. So everything is the same, except now we have 15 instead of 5. And so that's going to give us a higher price. We'll put that higher price into the calculator here. And note the payment will be 15, not 5. And in this case, we get 7.11. So that's less than the 7.19% yield to maturity we were getting on the 5% coupon bond. And that makes sense because with the 15% coupon, there's essentially more weight put on these earlier payments. So the upward sloping curve, the upward sloping term structure is going to cause the yield to maturity on this bond to be less. So this is just an important thing to keep in mind when you're comparing bonds of similar or the same maturities. They may have different coupons, and so you would not expect them in equilibrium to have the same yield to maturity. And generally, the yield to maturities will vary slightly depending on the coupon and the slope of the curve. So that's it. Let's finish up with some conclusions on the term structure of interest rates. So the term structure of interest rates, remember, refers to the relationship among interest rates for different maturities, all else equal. So currency, issuer, credit, all of those would be equal. So we're just looking at differences due to the maturity. The forward interest rates are the break-even rate of the interest rates between adjacent spot maturities. And the spot interest rate is the compounded average of forward rates spanning the same time period. Yield to maturity, now that's going to be on a bond with multiple cash flows, is the average of the spot rates corresponding to specific cash flows of a bond. So of course the yield to maturity on a zero coupon bond with a single cash flow would be equal to the spot rate, but in every other case they in general won't be equal. And then finally, yeah, as I just mentioned, yield to maturity for the zero coupon bond equals the spot rate. That's it. Thank you for listening.